Hello, and I would like to continue with another High Peak Education video lecture about circular motion and centripetal force. That is to say, we will be revisiting in a Calculus-Based Physics 1 class, Chapter 6, that is the chapter on Newton's laws, but now we will bring in this notion of centripetal force. Now if you saw the previous lecture video on uniform circular motion and centripetal acceleration, centripetal acceleration is a directional acceleration. But we know from Newton's second law that an acceleration also creates a force. In fact, a net force. So we're going to investigate that in this video. So let's first define centripetal force and its equations. So, as I already said, Newton's second law states that any acceleration is caused by a net external force. Therefore, a force must be applied to an object to keep it in circular motion. And I have you try to consider some examples in your mind. Okay, hopefully you pause the video and welcome back. So the idea is that you can imagine that if something's in circular motion, that a force must hold it in circular motion. If I whirl a ball on a string over my head in a horizontal circle, I think the force that's holding the ball towards the center is the tension force. Imagine a second example where a satellite is going around the Earth and the satellite is in nice uniform circular motion, maybe even like the International Space Station. You can imagine that the force that holds it in towards the center of the Earth is the universal gravitation force. Okay? So something has to hold it in circular motion. It needs a net force. How about a car that's on a flat circular racetrack? Well, that would be static friction. Not kinetic friction. I know the car is moving, but static friction, because the tires are not sliding side to side. And then lastly, what about a more difficult example? What if a car is like on a banked turn? I actually showed that in the previous lecture, but what would actually hold the car in towards the center? Now, believe it or not, it would actually be the friction force and the normal force, okay? Especially if the car is going a little kind of faster than optimal. I'll discuss that in actually these slides. And by the way, if a car is going too slow, the friction force will keep the car from sliding down that bank turn. But I'll say more about that as we go along. But anyway, there has to always be a force that holds objects towards the center of the circle or the center of the radius of curvature. And that force that helps to provide the net force is what is going to lead us towards centripetal force. Thus, the centripetal force on an object of mass m required to hold it in circular motion is given by this. Fc equals mac. And remember, AC is the centripetal acceleration. So from the previous lecture, we know that to be v squared over r. So F sub c, the centripetal force, is mv squared over r. So notice that a large force is required to maintain circular motion at a high speed. Well, that makes sense. If you double the speed, you get 4 times the centripetal force. And we talked about that in that it's harder to hold a turn in your car going fast than it is going slow. A large force is needed for a small radius of curvature. Again, that was discussed in the previous lecture. A smaller circle requires a larger centripetal force to hold it in towards the center because it's a sharper turn. Lastly, a large force is required for a large mass to maintain circular motion. And that should make sense because larger masses have larger inertia. Let's explain the centripetal force in a little more detail. Since the centripetal force vector, sorry, I said that wrong. Since the centripetal acceleration vector is equal to the radial acceleration vector toward the center of the circle, centripetal force should equal radial force. Okay? So this diagram where a ball is being whirled around a horizontal circle shows a radial inward directed force, and that's going to be at a certain radius, and then we can calculate the centripetal force. So here's Newton's second law. The centripetal force is F equals mac. So that's going to be mv squared over r equals F sub c, the centripetal force. Notice the sum of all the forces equals the net force equals the centripetal force. So notice the centripetal force is not a new kind of force. It's a new way to manifest the net force. So let me make a very vital pitfall prevention note for students. And I cannot tell you how many students have gotten this incorrect. So this is one of the few times in my slides I actually use red text, because if I've been kidding to this point, this time I mean it. Many people think that the centripetal force is a new kind of force. This is wrong. Rather, this shows a new role of manifesting existing forces as a net force. In other words, a net force that is center-seeking. In other words, never, ever put F sub c vector on the free body diagram. In other words, centripetal force, it's not in the list. It's not in the list of normal force, weight, tension, friction, and several other forces I'm sure that you've studied before. The centripetal force is a new way to manifest the net force. It doesn't go on the free body diagram. Net forces are revealed in a free body diagram from a force imbalance. So instead of writing F equals ma, we'll just write F equals mac whenever there's a centripetal force along that axis. Okay? So I hope that makes sense. This is a really important point as it relates to centripetal force. Okay, this example I will show in a later lecture, a later example problem video. So let us move on. Let's imagine that we examine centripetal forces for a car rounding a corner. If a car rounds a corner, suppose the top view looks like so, where the blue here is showing you the path, and the green vector is showing you the instantaneous velocity vector. And this is the top view of the car. The top view of the tire is like so, where when the car is, say, halfway through the turn, the velocity vector is tangent to the path, and the static friction force is always radially inward towards the center. This force is preventing the tire from slipping sideways. The rear view of the car is like so. So if we're looking at the rear bumper, notice that the static force of friction is inward. Okay? And its sort of contact point is the tires themselves. The full free body diagram should look like so, where the normal force balances the gravitational force, or the weight, down, and the static friction force is directed in towards the center. Notice we might call that the radial direction. But notice the net force, which isn't directly on the free body diagram, that's appropriate, but the net force is exactly equal to the static friction force. Because if we're rounding a turn, the static friction force is equal to the force that holds us in towards the center, prevents us from slipping off the curve, namely the centripetal force. Now again, I'll show another example of a car, but this time on a bank turn, and again, stay tuned for another example video. Now if a car is going too fast on a banked curve, consider a car going on a bank curve at a speed higher than its ideal speed. Then V0 should equal the square root of RG tan theta. I'll show why that is from the example video I'll show later. But in this case, the static friction must prevent the car from slipping up the hill. So the static friction is directed down the hill. Imagine this dashed line is the road surface. V is greater than VO, VO being the ideal speed. Notice the normal force is perpendicular to the road surface. The gravitational force is downward. So the net force is going to be some horizontal combination along the radial axis of the normal force and the static friction force. And the static friction must point downhill because the faster speed requires a large net force towards the center of the circle. The radial component of the static friction and the radial component of the normal force allow the car to make the turn. Maximum speed occurs when the static friction force reaches its maximum. Okay. Now, consider a car, and one more thing. The static friction, remember, is a value that can increase if you go faster and faster. When the static friction reaches its maximum value, the car is going just as fast as it can without actually starting to slip up the road. Now, how about if the car is going too slow? Well, the static friction force is going to be directed up the road surface because the car is going slower than this VO equals RG tan theta. In this case, the static friction must prevent the car from slipping down the hill. The normal force and the gravitational force are still in the same direction, but now the net force is pretty small because the car is going slower than ideal speed. So the static friction points uphill because without the static friction up the slope, a slow-moving car would slide down the incline. The normal force is radial, is too much radial force for circular motion when V is less than VO. Here, the radial component of static friction reduces the net radial force. Okay, so that's kind of the idea. All right, so non-uniform circular motion. What's going on with non-uniform circular motion? I discussed this before in terms of acceleration, but now I want to discuss this in terms of forces. We've seen that if speed changes, one can decompose the motion into tangential and radial components. So the tangential component is tangent to the path. The radial component is toward the center of the circle, perpendicular to the path. And the sum of those forces is the vector force sum. And notice that again, you could think about this like a right triangle. So since we know the total acceleration is the radial plus the tangential acceleration as a vector, the total force should equal the total radial force plus the total tangential force. The radial force is responsible for turning the car, for changing its direction, for the portion that's circular motion or even part of a circular motion. Whereas the tangential force is responsible for changing the speed, speeding the car up, slowing it down. And again, these kind of forces we looked at earlier in the semester. The radial part of non-uniform circular motion can be treated exactly the same as in uniform circular motion. The tangential part can be treated like linear forces from chapters 5 and 6, namely the Newton's Law chapters. So here's an example. How about a roller coaster car going through a vertical loop? Notice that this is the tangential direction and this is the radial direction. And let's assume this is a constant radius loop. Now, in practice, a lot more loops in real theme parks are more so teardrop shape. I could maybe discuss that at a later time, but for now, let's assume circular loop. Suppose the car is at the top of the loop. The centripetal force is directed towards the center because that's the net force. And the centripetal force, let's assume it's the same size at the bottom of the loop. Now, by the way, it wouldn't necessarily remain the same size because, the speed could change. In fact, usually objects, when they take a loop, the speed is greater at the bottom. So it's hard to tell here, but I think the centripetal force is a little bit larger at the bottom, and it is a little smaller at the top. Now, listen to me here for a second. This centripetal force should not be put on this free body diagram. I'm only showing it here for you so that you see how the vectors add together. Notice when you're at the top of the loop, the only two forces that are on the roller coaster car in the absence of friction and air resistance are going to be the gravitational force and the normal force. When you add the gravitational force and the normal force together, you get the centripetal force, namely the net force. In other words, the object is not moving very fast because it should be normal force plus mg, the weight, equals centripetal force. Whereas, so if you wanted to solve that for the acceleration, you would just divide by mass. Now, how about in this case? The normal force is in the opposite direction of the weight force. That is, the force that holds us towards the center, the normal force, is in the opposite direction of mg. mg doesn't change, but the normal force does, because depending upon where you are in the loop pushes you towards the center of the circle a different amount. And notice that the normal force will be much greater than the gravitational force to hold us in towards the center. Now, by the way, as weight does work on us, remember, this is why we covered this chapter after we talked about energy. Weight is doing positive work. Why? Because the weight force is speeding us up in this direction. So the car is going faster and faster. The centripetal force should be greater at the bottom than at the top. But the idea is this. If the centripetal force is large at the bottom, we need a very large normal force, quite larger than it was before, to hold us in circular motion. And if you write this down, normal force minus weight equals centripetal force, notice that you'll have a much larger centripetal force because the velocity is going to be much greater. Okay? So you should be able to work that out using Newton's second law. And in fact, I'll show that for this non-uniform circular motion example. Objects that go in vertical circles must take into account the force of gravitation. So I'll show this Tarzan problem also. I also want to pose to my class a challenge problem, which I think is quite an interesting problem. So I want to know, what is the minimum height, h min, as a rational multiple of r, okay? And when I say rational multiple of r, I actually mean capital R here, the radius of the loop, that the roller coaster car needs to complete this loop, starting from rest on this frictionless track. Notice that, in other words, if we allow this mass to just slide down, what is going to be the minimum height we have to build the first hill to in order for the car to make it all the way through this loop? Okay? And it turns out that it's not necessarily what you'd expect, at least unless you work through the calculation. Now I finally want to talk about reference frames and fictitious forces. When one is in circular motion, one feels a force pushing them into the curve. When one is slowing a car, one feels a force pushing them into the dashboard. Okay? These forces that one feels are not the real forces. You sense these forces because you think you are in a non-inertial reference frame. Because you are in a non-inertial reference frame. In other words, we think we are stationary, but we're actually in a reference frame that accelerates. So non-inertial reference frames are those that are accelerating, like the inside of a car on a curve, the inside of a car slowing down, or on our curved Earth. So what I will show in a later video where I perform intuition is I will show how when we move over the Earth, especially over large curved distances, the Earth produces an apparent force, and that's because the Earth itself is rotating. Inertial reference frames are those that are not accelerated. So inertial reference frames are frames in which we can all agree on the physics. Okay, so that's what I mean. Now, what is the centrifugal force? Again, this is not the real force. Someone on a merry-go-round would say, if you talk to them, that they feel an outward directed force pushing them away from the center, especially if it's going very fast. This fictitious force is known as the centrifugal force. So this is from the merry-go-round's rotating frame of reference. In other words, if you take a ride on this horse, you feel like you're being pulled outward. But in the Earth's frame of reference, there is no outward force. So the inertial frame of reference, the resting reference frame, the reference frame that is not accelerating, a person needs to apply a force towards the center to hang on and be in circular motion. In other words, the horse is being held in towards the center. A person might feel like they're being flying off outward, but the horse is actually being held in towards the center because it's mounted to the rotating turntable. Okay? And that's the idea. Okay? So what the centrifugal force is not. Consider a ball attached to a rope moving in uniform circular motion, constant speed. Suppose we cut the rope. What path does the ball take? Now remember, I showed this in a previous video. If you cut the cord, the ball should fly off in a straight line. Why is that? Because the net force is towards the center. The net force is the centripetal force. The tension force is manifesting itself as the centripetal force. And as a result, if we cut the cord, suddenly we don't have a centripetal force. So Newton's second law stops, that there's a net external force, ma, and the A is A sub c, the centripetal. So Newton's first law takes over, that an object in motion should stay in motion in a straight line unless acted upon by an outside force. So this ball should fly off tangent to the circle in the direction of the instantaneous, or that is the tangential, linear velocity. Now, if you were to consider a centrifugal force, in other words, if you were a ladybug strapped to the ball here, you might assume the ball would fly away from the center because you're feeling this sort of outward force if you try to think in your brain that you're an inertial reference frame. But this is the wrong way to think about it. Newton's first law says the ball would just continue moving tangent to the circle in a straight line. All right, everyone, thank you very much for your attention. I hope that lecture was helpful. Please smash that like button if you enjoy this content. Please share this video with people in your sphere of influence. Please subscribe to the channel to grow the channel. I want to thank you for your attention. And for another High Peak Education video, I'll be signing off. Thank you for watching, and I will see you in the next video.